All right, hello. My name is Li Yang. I'm here with my co-speaker and also manager, Andy Feng. I'll be doing the entire talk today. And today, I'm going to talk to you about TensorFlowOnSpark. This is a platform that we at Yahoo open sourced back in February of this year. So I'll give you guys a kind of overview of what it is if you haven't played with it. Give you a update of what we've been doing since we've open sourced, and then, if time permits, attempt a live demo. Okay. Now, if this would actually click, funny. There we go. Okay. So what exactly is TensorFlowOnSpark? Literally, it's the ability to run TensorFlow applications using Spark to launch your TensorFlow nodes. Quick show of hands, how many of you guys have actually used TensorFlow already? Oh, wow, okay, good crowd. All right, so if you use TensorFlow, you already understand that you're essentially defining deep learning algorithms, applications using kind of a high-level mathematical operations in the form of a graph that you define. And TensorFlow then manages the low-level details of shipping bits around, especially in a distributed manner, if you do distributed TensorFlow. And it handles all the low-level systems, shall we say, plumbing of getting data between the nodes. Spark, if you're aware, is a kind of in-memory version of MapReduce, and it does much the same thing except for just general data operations. Maps, reduces, it takes care of the underlying code. So why did we work on this thing at Yahoo? So first of all, Yahoo has historically been a large champion of open source, and specifically the Hadoop ecosystem. We actually open sourced Hadoop way back in 2006, if anybody remembers that. We've been an early adopter of Spark itself. In fact, Andy actually was one of the keynote speakers at the very first Spark Summit back in 2013. And specifically, our team has also been working on ORPC, which is another deep learning on Spark library. And in fact, our team will be giving an update on that Wednesday, tomorrow at 12:20 as well, by middle in June. So as a supporter of open source, Yahoo has obviously built out large production clusters for all of our data. We have tens of clusters, we have thousands of nodes per cluster, petabytes of data on these clusters. And so obviously we would like, actually our researchers would like, to be able to get access to this data inside TensorFlow. So before TensorFlowOnSpark, this is essentially what your kind of deep learning system would look like. You would have your production Hadoop cluster over on the right. You would be gathering data from whatever upstream data sources you might have. And then in our world, our researchers built their own little cluster for TensorFlow because they needed GPUs, because they needed whatever dedicated hardware, different versions of software. And so they would end up actually copying large chunks of data over to this little cluster on the left side. They do all their coding in TensorFlow, all their training, and eventually they would get to a good model, and then they would have to now ship the model back over to your Hadoop cluster and then try and apply it over there. So you can do this sort of at a small scale and maybe in an ad hoc manner, but obviously you don't want to do this full-time in production mode. So we want to go to more of a model that looks like this. And this is from our blog post. Basically, we would like to host TensorFlow on the exact same clusters that you host all of your other production data. We'd like to expose that data via Spark to all the other nice things that are built on top of Spark, including ORPC and even MLlib, Hive, and Spark SQL. So one-stop shopping, essentially. So this is, again, from our original open source blog post, and it demonstrates training the Inception image recognition network that was published a while ago. And you can tell by this graph, if you look at the one worker in red, it's taking somewhere around 45 hours to train. And if we double that, it comes down to something like 22. We double that again, we're down to 13, 14. And you can see that it's generally linearly scalable. The reason we ran this little benchmark is not necessarily to prove our TensorFlowOnSpark, but to prove that TensorFlow itself was linearly scalable. They had published benchmarks on that. And we ran this to prove that by running it on top of TensorFlowOnSpark, you're not taking a large hit or anything like that. So it's generally near linear scaling, much like TensorFlow. OK, and then back in February, we also published a little patch to the core TensorFlow to enable RDMA instead of gRPC. So we were actually running RDMA over InfiniBand networks. And again, if you could look at this graph, the default gRPC over Ethernet was taking something like, what, 220, 230 hours. And to run it over RDMA, it's now down to 100. Now, obviously, because RDMA is kind of a networking technology, shipping the bits faster, this gain is mostly applicable for deep learning networks that are very network intensive. So if you are moving lots of bytes around on the network, this is a potentially good way to speed it up. OK, so, sorry. Yeah. OK, so at the time when we published the RDMA patch, our friends over at Mellanox, who ship InfiniBand hardware, did their own independent benchmark of the code on TensorFlow, and they basically came up with similar results. For network-heavy operations, it's a little bit more than 2x faster. OK, so when we set out to build TensorFlowOnSpark, we had a couple design goals in mind. Obviously, we had looked around the internet, the community, looking for something that would kind of meet our needs. And we actually didn't find something that fit what we wanted to do. And this is where we wanted to be. So first and foremost, we wanted to be able to take an existing TensorFlow application that somebody in science or research may have prototyped on their laptop. And we wanted to be able to deploy it to Spark and Hadoop with almost no change. A lot of the other solutions that we've seen out there tend to, want to, I don't know, drive the entire process or force you to change your APIs. We were trying to minimize that. And as a side benefit of doing this, we kind of get support for all the existing TensorFlow capabilities that might exist in that version at that time. Again, we're trying to stay out of the picture and just get you to TensorFlow on the grid. So we get natural support for synchronous and asynchronous. We get natural support for model and data parallelism that's built into TensorFlow. And even we can leverage TensorBoard almost, verbatim. In fact, actually verbatim. And then the other goal that we had is, obviously, if you saw that previous picture, where we want to run TensorFlow on production, we wanted the ability to very easily and quickly integrate any kind of upstream data pipeline directly into something like model training or model inference. So if you have upstream jobs running Spark or Hive, we'd be able to easily connect to that. OK, so this is more details of what TensorFlowOnSpark actually is. First and foremost, it's kind of just a PySpark application. If you've worked with PySpark, actually, I should step back and talk a little bit about this. So TensorFlow, generally, when you define your application, it's written in Python. The operations are, the high-level API is mostly written in Python. And the nice thing about Spark is it has the PySpark interface, which is all Python. So it was kind of a natural fit to just run TensorFlow from PySpark. And so we created a wrapper of your TensorFlow application code. It basically launches the TensorFlow nodes inside your Spark executors. And from then on, essentially the TensorFlow cluster runs. Okay? And as part of this, I mentioned connecting to upstream data pipelines. So we support that via this, the two different ways of ingesting data into TensorFlow. So TensorFlow by itself generally has two main forms of getting data into your execution graph. The first that they have demoed was feed_dict. So basically you define placeholders for where you expect data to come in, and then you define a feed dictionary that stuffs the placeholders in your graph. In our world, we have actually connected that feed_dict mechanism to Spark's RDD dataset. And then the other ingestion mode is actually TensorFlow being in charge of reading data itself. So TensorFlow with their ecosystem project has built-in capabilities to access HDFS directly. And if you want to use that, you can leverage it to basically use their TF record, Q runner, whatever, to read directly from your HDFS cluster. Like I said, we support TensorBoard. We can write that to HDFS so that you can actually access it before and after training. And then last but not least, and very similar to what I mentioned before, we want to be compatible with different versions of Spark and TensorFlow. We don't want to rewrite all your code or depend on specific versions of code. So to prove that, here are the environments that we've actually run on or tested on internally. Python 2 and 3, Spark 1.6, now 2.1. We started with TensorFlow 0.12. We're now experimenting with 1.1 and maybe 1.2 shortly. And obviously Hadoop, and actually we've played with EC2 and Mesos also. Okay, so this is a high-level overview of how it works. And if you're familiar with Spark, it should look very, very familiar. The driver is essentially your main code, your application that executes the logic, and it tends to delegate compute tasks to the executors. And in the normal world of Spark, these compute tasks would do things like sum, aggregate, reduce. In our world, our compute task is literally launching TensorFlow on that node, on that executor node. And then once we launch TensorFlow, we actually describe the cluster spec to each of the nodes, and they then connect up and start talking to each other as a TensorFlow cluster. Once the TensorFlow cluster has started and formed, that actual TensorFlow graph starts executing, and you can read data directly from HDFS. Okay, so like I said, we generally try and just start the cluster and get out of the way. So the bulk of it is just getting everything set up and launched. A little bit of what we provide is providing this feeding of data into TensorFlow. And then finally, might not seem so magical, but it's actually kind of hard to shut down TensorFlow. So this is another thing that we provided. Okay, so this is the high-level API that you might use if you were to start playing with TensorFlow and Spark. We provide a TF cluster object to start your cluster. We provide a train and inference API to let you essentially feed the RDD into TensorFlow via the feed dictionary. If you are using the other input mode with Q runners, then you can just ignore those two in the middle, because TensorFlow will start reading from HDFS. And last but not least, shutdown. The run API has a couple arguments. They are, in order, the Spark context. If you have Spark, you will always have a Spark context. The map function is basically the somewhat translated form of your TensorFlow main function. So all TensorFlow applications have a main function which kicks off the graph execution. We basically ask you to just change the signature a little bit so that it'll fit into this architecture. The arguments are the command line arguments that typically you would have already passed to your TensorFlow app or node when you ran it. In this world, we're collecting the arguments on the Spark driver side and passing it to the executors. Then we have, obviously, the number of executors, the number of those that we expect to be parameter servers, whether or not we want to run TensorBoard, and which of those input modes you wanted to launch in. OK, so this is a very, very simple, the simplest conversion that we did. It's an evaluation job for, I believe, well, one of our image recognition is actually, sorry, the TF-SLIM classifier. And this particular evaluation job is fairly simple. It's a single node. But this is essentially what it takes to convert a existing TensorFlow app into something that can run on your cluster under Spark. So the top part, you can see, is mostly just importing PySpark and importing our library. The next little part is, like I mentioned before, converting your main function in TensorFlow into a map function that takes the command line arguments and this little context object that we stuff full of metadata. The start cluster server is something that we have to kind of simplify the move from a single node TensorFlow to a distributed TensorFlow. In all cases, you'll need to start a TF train server. And so this just kind of wraps that up a little. And then last but not least, we start the PySpark job with our run function. So as you can see, this is the diff, right? So there's a whole bunch of code that actually runs TensorFlow. This is what we had to change. OK, so now I want to talk a little bit more about these input modes, because obviously this will be one of the first decisions you'll have to make if you decide to use this. First, like I said, for the Spark mode, essentially what's happening is Spark is in charge of reading the data from HDFS, and it will read it in the form of these RDDs. In the Spark land, it's a resilient data, distributed data set. And then we will then pass that into TensorFlow feed dictionary. So as you can see there, I modeled the two arrows to imply that there are two hops for this data. The other mode is TensorFlow, again, reading directly from HDFS. So what I would say is that if you are trying to integrate with an existing kind of Spark data pipeline and you have RDDs and you want to stay in that land, the Spark mode is a quick way to get there from your data pipeline to TensorFlow, but at the cost of that extra hop, right? Whereas TensorFlow, if you're starting fresh and maybe you just want to read directly from HDFS, that would give you as pure of a TensorFlow application as possible with fewer data hops. And just to kind of describe in more detail what these things are doing and why they're different. So in a typical whatever PySpark application, we have executors. The executors actually will have little Python workers inside of them to execute Python tasks. And in our world, what we'll do is we will run the TensorFlow workers and the parameter servers inside these Python tasks. And it's a little bit special for the parameter server. It basically, we want it to essentially tie up that worker, tie up that executor, so that later data feeding tasks don't land there, because this node is only there for the purpose of being a parameter server. And then the other nodes, we actually launch in the background in addition to a little queue, which allows us to then later on come back and feed data within that partitions. But I always forget this part. Once we launch the nodes, they actually will start talking to each other. Then we'll come back, we'll do the RDD map partitions, and it'll go into the two available slots that are in our cluster now. And as part of that, we will actually just be stuffing this queue that we've created. And then when TensorFlow runs and asks for data in the feed dictionary, it will literally just read off of that queue. Okay, and there's a little bit of magic between, for managing the queue and partitions, and that's kind of what we provide. And again, actually, one thing I wanted to cover here. So one of the things that we've seen a lot from some of our users is why do I need to specify the exact number of executors to match the cluster size? If you imagine that, say, we ran only the PS and worker 0 and we had a cluster of 3 nodes, then that RDD feeding task would land on that third guy and there would be nobody to listen for data there. So we actually ask that you specify in this cluster, if you need 3 TensorFlow nodes, you specify 3 executors. Okay, TensorFlow mode, much simpler. We literally launch everything just straight. They will connect and form the cluster. They will read directly from HDFS. So a couple byproducts of those 2 different models is related to failure recovery. So first and foremost, anything in TensorFlow, highly, highly recommended that you save checkpoints. You don't want to be 48 hours into training and then lose all your data. So generally, you want to regularly checkpoint so that if for some reason there is some issue, TensorFlow has the capability to restart your cluster and load your training and your model state from a checkpoint and continue from there. But in the 2 different modes, as you saw, input mode Spark, your workers are actually running in a background task. That means Spark knows nothing about it, really. So if those guys fail, you will not see anything about that. The good news is generally they only fail if you messed up your TensorFlow code. So you would see that very early in your development process. The other good news is that because of this, the data feeding tasks, which tend to be more numerous, if you're talking about shipping petabytes of data through here, those, if they fail, can be retried and sent to the TensorFlow node. On the TensorFlow side, because the workers run in the foreground, if those guys fail, Spark will actually naturally try and restart it, but it's a little bit tricky because it literally depends on how TensorFlow failure handling works. If you are on a non-chief worker, generally it'll load from the snapshot and resume. If you're on the, I think the parameter server would do the same, but if you're on the chief worker, I think it's chaos and you have to start over. Yeah. So again, something to consider if and when you decide to choose one of these input modes. Okay, so on top of that, so as we know, Spark, Hadoop, often you may have just nodes going down for whatever reason, hardware, software, or preemption. Right now, there's a little bit of a problem here because when we define the TensorFlow cluster, it's actually currently statically defined. If you've run distributed TensorFlow on your own private cluster, you essentially have to do something like a Bazel run with a list of here are my other hosts and ports. Obviously, that works when you're on a dedicated cluster, but when you're inside of Hadoop and Yarn and your job gets killed here and it gets restarted there, it's very hard to respawn that TensorFlow cluster on the fly. And even if you were lucky enough to land on the same hardware, the same physical node, a lot of times that port that you bound to originally has now been taken up by some other job. So what we need is something more on the order of dynamic cluster management, AKA if a TensorFlow node dies, how do we reinsert a node into the training live while restoring for a checkpoint? And we've been chatting with the TensorFlow team. They've got some ideas. Right now, they take advantage of, I think, Kubernetes to get some of this, but we'll discuss this in the future. Okay, so as I mentioned, we get pretty much free support for TensorBoard because we're literally just running TensorFlow. So this is just a screen cap of one of our MNIST jobs running. This is the execution graph. Additionally, you can instrument your TensorFlow code to add some metrics. This is just the accuracy and loss. And again, in the MNIST example, you can instrument, like display the images that are actually being read. And so you can see a couple numbers there. So, okay, so at this point, I want to talk to you a little bit about the typical application development process that we've seen with respect to TensorFlow, at least with our experience with our researchers. So most of the times they'll start with a single node, laptop or desktop. They will be prototyping TensorFlow, just straight on. And they'll copy a little snippet of data to that box to explore and build their network. They'll be using graph session, interactive session. These are the standard TensorFlow APIs that you run on a single node. And if you have not played with TensorFlow before, I highly recommend that you start here because there is a little bit of a learning curve and you don't want to try and learn 3 things at once. So once you've got a single node working, most people move on to multi-node or distributed because as we've all learned in deep learning, more data is usually a better model. So at this point, you would tend to start to use the TensorFlow distributed APIs. You'll start to see things like the cluster spec in the server. Again, what we're trying to do is kind of help you with some of this. You'll copy, a lot more data to your cluster, but you'll still be confined to whatever fits on those physical disks. And at some point, the scientists will get to a point where the model looks great, it looks promising, I want to get it to production. So hopefully, that's where TensorFlowOnSpark comes in. So at this point, we'll be able to deploy that same code to your production cluster with a couple API changes to start your cluster and shut down your cluster. Like I said, you can connect it to any upstream data pipeline, and you can connect your model to production data with TensorFlow serving. Okay, so I've got a little bit of time, so I will click out and demonstrate. Or not demonstrate. Okay, so this is our Git repo. And from the top level, you'll see that there's not a whole lot of code here. Mostly, the bulk of the code is actually in the examples. The actual TensorFlowOnSpark code is here, and it's, as you can see, very lightweight, where we don't intend to take over your world. Our intention is to just get your TensorFlow going. Okay. Under examples, we have converted a couple of examples that we found from the TensorFlow team or from the general internet. And the whole point of these conversions was literally just to kind of prove out that the conversion process was easy or doable. And as you can see, just about everything, basically everything we took a look at, we were able to convert without too much effort. Sorry. So this ImageNet code, if you guys are interested, is the exact same code that we ran for our benchmark. So if you guys want to benchmark your own hardware, feel free. This MNIST code is basically, we have different forms of the MNIST code. The Spark directory contains the input mode Spark variant. The TF contains the TensorFlow mode variant, and a little preview of streaming. Okay, so with that said, okay, back to here. So a couple common gotchas that we've seen with people who have been playing with this. As I mentioned before, we want you to kind of map a single node to a single Spark executor. This actually works much better in principle because simple things like your executor logs become your TensorFlow node logs, and it's a direct one-to-one mapping. If we allowed multiple TensorFlow nodes on a single executor, your logs would get all interspersed, and it would be a lot harder to debug. The second common gotcha that we've seen is HDFS access. So like I said, TensorFlow can access your HDFS directly, but with the help of native libraries and a couple jars or whatnot. So usually this has to do with LD library paths, looking for libhdfs.so. And then the last one, I get a lot of questions, which is, I have some algorithm, I converted it to TensorFlowOnSpark, why doesn't it scale? I threw it at more nodes and more hardware. So this is a kind of a large question. And the simplest answer is, if your algorithm is not seriously taxing compute, memory, or I/O, then throwing more hardware at it probably isn't the answer. And my trivial visual example of this is, if I want to print 1 to 1,000, that's going to go really quickly on a single machine. If I try and distribute it to 1,000 machines, probably won't be that fast. And so it's kind of, you can think about it kind of like that. You need a meaty problem that is expensive for a single node. Okay, so what's new? What have we done since February? So obviously we've had community contributions. We had one which was, again, compatibility with CDH. We have tweaked the data feeding for the RDD side just to take care of a couple corner cases and clean that up a little, and a couple bug fixes along the way. The RDMA patch that we submitted back in February is now actually been merged into TensorFlow under the contrib directory. I think it's scheduled to come out with 1.2 shortly. So if you guys want, that'll be directly available. We've also added the notion of a registration server. This is mostly to collect your hosts and ports for your cluster. One nice thing of having a registration server is that one day when we get into flexible dynamic cluster management, we might be able to tie it into that kind of thing. We've added Spark streaming support. So obviously the Spark guys have done a great job of adding Spark streaming APIs. They actually require not that much change. And then last but not least, we've added basically a pip package. So now you can do pip install TensorFlowOnSpark. So I'll talk a little bit about these last two. So this is a very simplified diff of what it takes to go from the standard Spark job to a Spark streaming job. And if you recall my little preview, we have the MNIS example set up for streaming already. It's available on our repo. So as you can see, it's mostly just converting and adding kind of whatever imports, changing the APIs from text file to text file stream, changing things like save as text file to save as text files. And so it's fairly minor. And we start the streaming, and then we shut down the streaming. So with that, you can essentially connect this up to Spark streaming. And this is what pip packaging does for us. So this is a command line that we have on our README about running the Spark demo. And before that red line, we asked you to check out the repo, create a zip file, ship it to the executors in the -- archives. And now, if for standalone operation, where you control the Python distribution on that box, you can do pip install TensorFlowOnSpark, and then remove the zip file. Okay, so I have like a couple short minutes maybe, or should I go for questions? I'll try it. Okay, so I will attempt a quick demo. So basically what I'm going to do here is take you guys through our wiki instructions for standalone. To save some steps, I've already got this checked out. And I'm going to go here. Yeah, I was working, getting there. All right, is that better? Okay, all right. So, yeah. Okay, so I already have Spark installed, so I'm going to skip that step. you can just pip install TensorFlow and pip install TensorFlowOnSpark. I've already done that, but I will show you that fact. So we have TensorFlow installed here. We have TensorFlowOnSpark installed there. Normally I would download the data, but since I'm running out of time, I will use the data that I already have. And then here is starting up our standalone Spark cluster. Hopefully that will start up nicely. So this is a fairly small cluster, just 2 nodes. We can go to the Spark UI. You can see that I have 2 nodes running. Wow. Okay, sorry about that. Okay, and then I'll skip that part. And we don't need to convert the MNIST data files because I already have them. And this is literally running the training, and I'm going to do a little bit more than that. Steps 10,000. And I'm going to try and run TensorBoard. Okay, so this will run our basically Spark input mode, MNIST. You can see it running and starting nodes. There is my TensorBoard URL, which I can click on. It'll be empty initially because it's still going. We can look at our Spark UI. You can see that this is a standard Spark application. This is running. So you see this first job is literally launching the 2 nodes, and you'll see that it's partially completed. That's because one of them launched the worker node and came back immediately and finished. The other one launched the parameter server, and its job in life is actually to block that node from the data feeding tasks that are now happening on the second job. So you'll see that the data feeding tasks are going. If we look at our TensorBoard, we see that now we're getting data. We see that the accuracy is climbing. The loss is decreasing. We can hopefully see some images showing up. It's fun to look at handwriting every now and then to see what the computer has to suffer through sometimes. But you can see that it's reading digits and data, and here's your graph. This is your execution graph in TensorFlow. Like I said, as you're getting used to TensorFlow, this is probably the best place to start, just to kind of understand what your code is doing, what the flow of the tensors are. Okay, so that's my quick demo. And wrap it up, hopefully. Oh crap, I'm out of time. Okay, so what are the next steps? So we've been tracking high-level APIs with TF-Keras. We're, like I said, working on failure recovery with dynamic management. And that's our summary. We're bringing deep learning to big data clusters. Any questions? Thanks to all these people, by the way. I don't have time. Thank you.